what happens when we do restore order to the carbon? And the fact is, we restore order to the ecosystem as well. And so that's where I get the title. Next slide. This analysis is based on the second law of thermodynamics. You may recall, if you went to school the same time I did or later, that the second law of thermodynamics says that every process that goes on in the universe creates disorder. And the conclusion, if you accept that premise, is that everything in the universe is eventually going to become disordered. And you get a condition known as a heat death, where there's no energy, no usable energy left. There's a lot of energy, but it's not usable anymore. So now, in the past 50 years, thermodynamics has evolved. And modern thermodynamicists see it differently. A system to remain ordered has to discharge the entropy that it creates. And as long as it can discharge the entropy that it creates, it can remain ordered. A system isn't doomed to disorder. A system is just required to discharge enough disorder to keep itself ordered. And that's the little diagram that I tried to represent over there. Yeah, the Earth has to discharge enough disorder to get rid of all the disorder it's creating. So now our world is a complex ordered system that discharges more disorder than it generates, and I'll substantiate that later. Thereby becoming more elaborately ordered all the time. Now, does that sound familiar? There was a scientist a long time ago that figured the Earth was getting more ordered all the time. Do you remember who he was? Charles Darwin. That's essentially what evolution is. And that fits right in with the thermodynamics. And that fascinates me too. Next slide. And how does that fit with sustainability? These days we're all excited about keeping the Earth sustainable so that our offspring can live as well as we can. And so how does the second law relate to sustainability? If a system or process may be unsustainable because it runs out of raw materials, or because it runs out of energy, or because it accumulates too much waste material. This is a material balance issue. And it's based on the first law of thermodynamics. The first law says matter and energy is neither created nor destroyed. So that what comes out of a process is the same matter and energy as what goes into the process. But because every process has a lot of different materials, it's hard to tell which one might run out and which one might not. So it's hard to define what's going to keep a process sustainable and what's not. So a process can be unsustainable for any number of reasons. Next slide. This fascinates me. If a process runs out of order, order keeps a process functional, and I won't go into that too deeply, but a process can only function if it's ordered. This little sign comes off a vending machine, out of order. What does out of order mean? It means it doesn't function anymore. It's out of order. So in addition to everything else it implies, sustainability requires that a system be able to continue functioning of all its processes and still remain ordered. See, this creates entropy. This requires that the entropy not accumulate. So you've got to be getting rid of it. To be sustainable, the Earth must be able to reject the combined disorder of all its many processes. Now, an interesting side note. Carbon dioxide in our atmosphere impedes the discharge of disorder. So when we put carbon dioxide in our atmosphere, the Earth can no longer discharge a disorder. So the disorder starts to accumulate. So all the nice ordered things that we're used to, all the evolved ecosystems, can no longer sustain themselves because they're falling apart. There's too much disorder. So that's basically what this is all about.
Can I
So
ask a question? I'm really stuck on how are you defining disorder?
I'll come to that.
Okay.
Yeah, I know that's confusing.
I don't understand this until
I got lots of I got lots of criticisms about how I can't understand this unless you explain and define all these things. And if you've got 2 or 3 hours, we can do it. But I will get to that, and maybe it'll help. Let me just make a comment on it. If I take two molecules one over here and one over here, and they randomly move around, and I can't tell really where they are. As soon as I attach them together, then at least I know where one is with respect to the other. That's order. If I might tell a story of the blind man I knew. He lived in an assisted living facility that closed down in the summer. So when I was a kid, he used to come to live at our house for the summer. Well, if I slept in his room, it didn't really matter whether it was day or night. He knew where everything was. At night, I was like the blind man. But the order in his room kept it so he knew where everything was. And that's what I mean by order. And I'll try to be more specific.
No, I'm just, it's me, not you.
Bigger molecules are more ordered than smaller molecules. Molecules that are attached together are more ordered than molecules that are independent. And so we'll get into some of that. So let's go on to the next one. But this is interesting because it implies function, that order relates to function. So let's go on to the next. Okay, so what is sustainability? To many, sustainability means recycling and reusing all possible resources. But using less just slows down our approach to the ultimate total disorder. You can't reach a point where you're using nothing. And to be sustainable, you must be able to close that loop altogether. You must be able to discharge all the disorder or reinstate all the order that you've used through your metabolism, your lifestyle, your social and cultural and industrial activities. All that disorder that you've created has to be regenerated or discharged in order to maintain the order of your system. So let's go on for that. Now, order is so important. Maintaining order is an existential issue. We simply cannot exist without it. Loss of order means loss of survival. If an individual organism cannot discharge enough disorder, it dies. If a species cannot discharge enough disorder, it goes extinct. If an ecosystem cannot discharge enough disorder, it collapses. If a planet cannot discharge enough disorder, it cannot support life. And there's some very interesting references here that I can refer you to. But life is natural. It emerges, evolves, and thrives as long as the conditions are right and the planet can discharge the disorder. So let's go on from there. Biomass is the most ordered form of matter known. It's what's left after the disorder from the process of making it has been discharged. Without discharge of disorder from the photosynthetic process, the assembly of the cellulose molecule would not be possible. The bottom picture is a small part of a cellulose molecule. For the Earth to retain this kind of disorder, it must discharge excuse me, to retain this kind of order, it must discharge massive amounts of disorder. And a side note is that if the Earth is to remain order, it or we must preserve our biomass. Destruction of elegantly ordered biomass to make energy and carbon dioxide destroys the ordered nature of our planet. So, next slide. Phase changes are step changes in disorder. Disorder can be generated, continuously, or it can be created discontinuously. When ice melts, it discharges a whole hunk of disorder all at once. This is a melting glacier, and there's a lot of disorder being generated there. You're taking the ordered ice, and you're making disordered water from it. Water is far more ordered than steam. Evaporating water consumes a whole lot of order and produces a whole lot of disorder. This is a desert, and all the water has been absorbing disorder and dissipating into the air. So the general disordering process has those kinds of effects. Next slide. Ecosystems are an expression of disorder. This is a mature ecosystem. This is an immature ecosystem. It's a nice farm. It's one of the reasons we're in trouble, because to our perception, is this more ordered than that? Is that more ordered than this? It goes to your point, right? No, this is far more ordered than that is. And it comes down to, let me use the term complexity, because this is a very complex form of order. And the complexity has been removed here. And maybe in the interest of time, I'll save that discussion until later. But mature ecosystems are a whole lot more ordered than immature ecosystems.
If I could just have some people in the room have visually impaired, rather than saying this or that, you can say this forest is much more
Oh,
than this field.
I'll try to remember.
We did have it for all of us.
I'll try to remember. Okay. For those of you who are concerned with soil carbon is an expression of order. Most of the soil carbon that we're talking about is living matter, and that's an extremely ordered product. When you remove that order, you have soil that looks like that, but it has no order left. Disturbed, contaminated soils are a whole lot less ordered than living soils. Soil biology is a manifestation of soil carbon, so highly valued by Soil Carbon Coalition. Okay.
I might just comment that what Don is talking about is not the order of even rows, but a chemical complexity.
Yes, actually, yeah, when you talk about complexity, in a way, the even rows eliminates a couple of dimensions of complexity. Those rows could be twisted and turned, and they'd be even more ordered, but they'd look disordered to us. Now, through evolution, nature has been increasing the order of the Earth for millions of years. And that goes back to, maybe it was my second or third slide, where I said that Charles Darwin is the guy who contemplated how this order manifests itself on Earth through evolution. If we want to live sustainably, we have to do all we can to maintain and expand the order of the Earth. Building upon what nature provides, we must encourage the processes that generate order and create the conditions that discharge order. Now, I take a little exception to myself. These conditions are not generating order. They're really generating disorder, but what's left behind is order after it's discharged. So this This is where the big issue is. How do we get rid of this disorder that we're creating all the time? And it's through processes like this. So let's go on.
Say what the process is, right?
Oh, sure. Oh, because, I'm sorry. I'm a slow learner. Yeah, we have to decrease greenhouse gas concentrations in the atmosphere. We have to restore our ecosystems. We have to restore our soil carbon, which these two are more or less the same. We have to cultivate soil food webs. Again, these are all related. Increase biomass and restore hydrology. So all of those. Okay, now I want to talk about global warming. And this is a conceptual thing, so bear with me. Present science sees climate change as an energy balance phenomenon. Now, just let that sink in a little bit, because there's an alternative point of view that I want to express. But let's first talk about global warming as an energy balance. Next slide. Climate change is currently being presented as an energy balance phenomenon. Okay, here's a balance. Energy is coming in, energy is going out. Whether the Earth stays cool or not depends only upon whether these two are equal or not. If there's more energy coming in than is going out, the Earth warms up. If there's more energy going out than is coming in, the Earth cools down. And there's really nothing else you have to consider when that's your point of view. There's more than that to consider in my point of view anyway. So if I read all the way down this, oh, well, people have been working on this for years and years and years. And they've learned that the sun emits energy in variable cycles. And so they said, you know, when the sun emits more energy, the Earth warms up. Okay. And when the sun emits less energy, the Earth cools down. Okay. But if the outgoing energy is impeded, such as you have carbon dioxide in the atmosphere, then the Earth can't discharge its energy anymore. So energy is beginning to accumulate. So that also makes the Earth warm up. So variations in incoming and outgoing energy flows cause global warming and or cooling, which they say is climate change. Good, that fits. That's consistent argument. Everything's fine. Let's go on to the next stage. This little diagram kind of says the same thing. The sun emits energy. It impinges on the Earth. The Earth warms up. The Earth starts to emit energy in proportion to the fourth power of its temperature. And eventually the amount of energy it's emitting is as much as is coming in, and it stays constant. The temperature stays constant. If we put CO2 in the atmosphere, it reflects some of that energy back, and the Earth warms up. So this is a pretty consistent argument. Milankovitch is a guy that studied all the cycles of the planets and when we would receive more or less sun, and he found it a little bit cyclical, and that seemed to match with times when the Earth was warm. And so this argument has a lot of support. Let's go to the next slide. So in this view, the sun emits energy, it goes through the Earth system and is re-radiated into outer space. And this is okay, and it's accurate if the Earth is considered to be a single unified system that energy flows through. Now let's look at it a different way. The second idea is an entropy balance. Climate change as an entropy balance phenomenon. Okay, let's go on to the next. What happens if when the energy gets here, it doesn't encounter a single unified system of energy transfer, but it encounters multiple interdependent parallel flow paths. The energy balance explanation would be correct if there was just one system it was working with. But the Earth has lots of different systems capable of carrying energy across its surface. The atmosphere, the hydrosphere, the biosphere, and all of these systems, and there are many more, and all of these systems operate independently or interdependently, and they transfer solar energy. The solar energy encounters a certain amount of resistance passing through each of these systems. And when the resistance of a system changes, the proportion of energy that it handles changes. At this point, let me just interrupt and tell you one more thing about the reason I got into all of this. And that was, it became clear to me that there was a relationship between global warming and the amount of biomass on Earth. And it was totally independent of the amount of carbon dioxide in the atmosphere. And I thought I was going crazy, which is why I talked to several biologists and ecologists, and it was hard to bring them my attitude because it was different. But I'm satisfied enough now so that I think I can present this rationally. When the resistance of the system changes, the energy carried by that system changes, and it leaves less energy to be carried by the other systems. So the proportion of energy carried by all the system changes if the resistance of one system changes. So let's go on to the other. Okay, here's our system now. The sun emits energy, and it's divided between the atmosphere, the hydrosphere, and the biosphere, and all of these systems discharge into outer space. I think we can go right on. Now, each of these pathways is a natural machine. If you're familiar with thermodynamics, it started around the 1850s or maybe before. And it involved the transfer of heat through a machine and the creation of work by the machine. Work is energy with order. Entropy is energy without order. So the machine can create order and do work. Order and energy is work. So when it flows, these are different kinds of order. When energy flows through the atmosphere, it creates an order system, something like this. This is a convection cell. The Earth, or the bottom plate, gets warm. It heats the air rises, goes up to the upper atmosphere and cools off, and expands because the pressure is lower up there. Circulates out. As it cools, it gets heavier and circulates down again and comes back in. So you have this regular cycle of bulk flow. I'll emphasize that statement, bulk flow. Fully entropic or fully disordered flow is like conductive flow. There's no current. It's just one molecule batters against another molecule, and that kind of travels along as a wave. But in bulk flow, the actual material flows. The air actually rises and circulates around in this. So this is the kind of order that's created by energy flowing through the atmosphere. In the hydrosphere, you have another type of order being generated. This is moisture in the air condensing, usually associated with this kind of, and that condensation utilizes a lot of order. This is a very ordering process to condense and to start to precipitate as rain. You've gone from the volatile phase, from the gas phase to the liquid phase. That's a a creation of order. And it's different for the hydrosphere as from the atmosphere. In the biosphere, you have photosynthesis, which takes carbon dioxide and water, and it creates sugars, and it polymerizes the sugars, puts them all together to create solid biomass. And this is a massive ordering process. All three different types of ordering processes. Okay, let's go on. Oh, no, go back. This is a little bit of my fantasy, but even just a water droplet can be viewed as a thermodynamic system. And when energy enters it, the light rays are refracted, and they come out in an ordered form with all the red ones in one place and the yellow ones in another place and the green ones and so on, and you get a rainbow. Energy, when it passes through this kind of a system, creates order. And it may create order by just separating the types of disorder, but that's a fact. Okay, let's go on. Here we go. The scientific name for disorder. Entropy content is a thermodynamic characteristic of a system. It is a function of the heat content of a system and the temperature. S is entropy, Q is the heat content, and T is the temperature. Well, just to help you visualize this, if I have 100,000 BTUs of heat, and it's at, say, 1 degree, I then have 100,000 BTUs per degree of entropy. But if it's at 100 degrees, I only have 1,000 BTUs per degree of entropy. And that's all at the same heat content. So that a higher temperature implies that you have less entropy involved. And that's just good to keep in mind. A high entropy content indicates a disordered system. Now, this is hard to visualize, but if you have order in a system, you can make that system disordered, not by removing any material from it, but by removing disorder from it. By removing this combination of things, that system will become ordered. The size of the molecules will grow. The placement of the molecules will change, so that you'll begin to differentiate between different types of matter. And a low entropy content indicates an ordered system. I may have had that backward. When you take entropy out of the system, you make it ordered. You increase the order. So that, and the note is just that a given amount of heat contains more entropy at a lower temperature and less entropy at a higher temperature. And that is significant later on. So let's just go beyond this, trying to keep within my time frame. Things to consider about disorder. Entropy can be removed from a system, making the system more ordered. Now, that's not intuitive. It's very hard to grasp. But when entropy is removed from a system, it becomes ordered. Or it can be added to a system, making it disordered. And this kind of goes without saying, but again, we're playing on the very edge of intuitiveness. A system that is already maximally disordered can't accept any more disorder because it's already maximally disordered. A system must be ordered to take on disorder. It can't be maximally disordered. It has to be partially ordered. And the more ordered a system is, the faster it can take on disorder. Mm-hmm.
example just to wrap my head around.
Yes, yes. Everybody says that.
I've got a bit of entropy in my brain right now, but
Yeah.
a system that is maximally disordered.
Yeah.
Can you give an example of a system that's maximally disordered?
That's going to take a little too much thinking. I'll try to approach that, but it'll slow me down.
Can you give an example for the first two?
Well, okay. Let's go back a slide.
An example of maximal disorder would be white noise.
Yes, good. Okay. Or white light too. I showed you the water droplet and the white light coming in, and the ordered light coming out. When energy comes toward the Earth from the sun, it carries entropy with it in the amount of the energy over the temperature. So the energy from the sun coming into the Earth brings entropy with it. That's a disordering effect. Okay, it heats the Earth up. The molecules start to move faster, and it's just a disordering system. You can't tell where they are if they're moving too fast for you to see them.
How about like after a hurricane comes through and Florida is just wreckage everywhere and there's maximal
Yeah.
like that?
I hesitate on that. There's a lot of people who liken thermodynamics to a child's room. It becomes disordered when the child lives in it for a little while, but you have to put energy into it to clean it up, and then after you've cleaned it up, it's clean, and that's low entropy when it's clean, and it's high entropy when it's disordered. That's a little difficult because the logic is a little bit skewed there, but.
I wonder if photosynthesis, a plant giving off oxygen in individual atoms, right?
Mm-hmm.
But it's creating, is the oxygen and the transpiration, are those discharging disorder in order to create the cellulose and the...
Well, the oxygen carries away a lot of the disorder from that reaction, yeah.
And in doing that, it can create order in itself.
Well, yeah. The reaction of the carbon dioxide and water creates biomass, which is a very ordered material. So the biomass carries a lot of order. The oxygen carries a little disorder out of the way. But the total order balance, which I'm getting to, is
In your formula, could you say what the S and the Q stand for?
yes. This is entropy,
Oh,
and this is heat. This is essentially energy.
energy divided by temperature.
Right. Okay, let's.
Just a quick example, Mike. An oak log is highly ordered. If you burn it and turn it into ash, smoke, CO2, carbon monoxide, a mixture, and a relatively unordered mixture of everything like that, you increase the disorder.
Got it. Yes. Wish I thought of it. Okay, let's go on, and we can go beyond this too. Now, only recently have we been interested in non-equilibrium thermodynamics. Equilibrium is maximum entropy. And maximum entropy is where nothing has any differentiation left. It's all kind of uniform and disordered. And when you only study when you only study equilibrium systems, you're not getting to the heart of the matter, because we live in a system that's highly ordered. So we don't We don't live in an isolated system, but isolated systems tend toward equilibrium. Our system tends toward order, and I think I'll get into that soon. So this new law of thermodynamics says that each system will take on as much energy as it possibly can in order to generate the maximum possible entropy, because the universe tends toward disorder. So the disorder is a driving force for things to happen. Well, it's really the other way around. Order is a driving force to push things toward disorder. So our natural machines will compete with each other for solar energy. Each one will use as much energy as it can and leave the rest for the others. Okay, let's go to the next slide. I decided to talk about entropy balances. All the entropy generated by the natural machines in the system must be removed from the system to preserve the order level in the system. So everything that goes on around us is generating entropy. And that entropy has to be gotten rid of. Let me just interject here, something that I maybe should have, but you remember the astronomer Edwin Hubble, the Hubble telescope. Well, Hubble's great contribution to astronomy was the recognition that the universe is expanding. Well, where is all of this entropy going? The Earth has got to get rid of this entropy. Well, isn't it going to fill up something if it just keeps dumping it? Well, apparently not, because the universe is growing faster than the entropy that we discharge can fill it. So the expanding universe, the increasing size of space, is enough to keep this entropy ejection machine going forever. So this fits in with modern science and all of that. So let's go to the next one. So now we've seen our three machines. But what happens if we pave the parking lot and destroy some of the operation of the hydrosphere? Well, there's some extra energy going on here that somebody's got to take up. The biosphere is probably not going to do it because it depended upon the water created by the hydrosphere. So the atmosphere drew the short straw. So the atmosphere is going to be handling more energy because the hydrosphere didn't. So you get more excessively large, violent convection cells because of the extra energy that the hydrosphere is expected to handle. Let's go to the next slide. If the biosphere is damaged, and we do that when we cut down half the forests in the world, they're not going to be able to handle as much energy. And that gets dumped on the atmosphere as well. So when the Earth runs out of biomass or diminishes its biomass, the atmosphere is definitely affected. And this relationship is going on all the time. When you talk about global warming, somehow maybe the atmosphere can't handle that amount of energy. Well, one of the ways it can handle that amount of energy is by warming up. When it's hotter, it's going to be transferring more energy.
Why can't the hydrosphere take on the extra energy again?
Well, because it's damaged too.
Hydrosphere?
Yeah, I mean, we have, as I say, paved the parking lot. Was it paved paradise? Put it on a parking lot. Yeah. And so these two are being kind of mutually destroyed. So, yeah, carbon dioxide makes a difference. But the fact is, we're biasing the balance of the machines and putting it all on the atmosphere. And the globe is warming up because of that. We can go on to the next one. I didn't know I was so repetitive. When they're both functionally damaged, their combined energy deficit must be accommodated by the atmosphere. The Earth will warm up until, that's what I was saying, the Earth will warm up until the atmosphere reaches a temperature at which it can handle the additional energy load. When the atmosphere takes on the additional energy load, its operation becomes more erratic, dynamic, and violent than it was when it only had to handle the original residual energy. So this is my relationship, this is my reason why it's clear that it's the destruction of these two machines that leads to the increased temperature and operation of the atmosphere. Okay, so now, okay, these I think we've gone over. These are how do we know the hydrocycle is diminishing? I don't need to add to this. Let's go on.
Just say that's all of the stuff we just.
Oh, okay, yes.
30 days, yeah, we don't have to.
I noted the reduction of haze, the reduction of nucleation, the enhancement of visibility. You know, when the haze is gone, you can see further. The relative humidity is higher. And there are desert biomes in California, Mexico, the Mediterranean, all of which are growing. And the expansion of deserts, the Sahara, the Gobi, and the Great Basin of the United States, these are all expanding deserts, and groundwater depletion in these major aquifers. The Ogallala, which is in Texas, Oklahoma, and the Midwest. The Floridian Africa, Floridian aquifer, which is under Georgia and South Carolina and Florida, and the Central Valley in California. And they're all distinctly diminishing in size. Indicators of biomass deprivation, degraded biomass cover, reduced soil carbon content. The fact that we're using biomass for more things, we use it to make tools and construction, we change the use of the land by destroying the biomass on it and making way for agriculture. We use the wood for fuel. We generally destroy our ecosystems, and we change the fuels that we use. We're no longer using current fuels, we're using fossil fuels. This is an indication of our consumption of carbon. And this, you would think, using less current carbon would tend to reverse the process. But it really hasn't. Or if it has, it doesn't show yet. Hydrologic cycle changes, reduced soil permeability, flooding, aridity, desertification, climate change, temperature escalation, storm intensification, climate diversity reduction. This word diversity I want to go into in some detail if I have time later. Biological diversity reduction. Okay, both climate and biology are experiencing severe limitations in their diversity. And that's all thermodynamic. So we'll go on to that later. I was concerned about this idea that I had that the biomass was, the Earth was deprived of biomass. And some of my studies gave me a curve like this. And I owe these data points to a guy named Václav Šmil. He's a Czechoslovakian immigrant is at the University of Manitoba in Canada. And this scale is 20,000 years. This scale is 1,000 gigatons. And 20,000 years ago, the amount of biomass on the Earth was about 550 gigatons. By about 10,000 years ago, the biomass on the Earth had increased to 1,000 gigatons. It had doubled. And then it kind of tapered off. And by 250 years years ago, it was down maybe 100 gigatons. And at that point, the bottom dropped out, and it's been plummeting. Till today, there's only 610 gigatons, and that's a typical figure in all the literature. So that seems to indicate that the Earth is biomass deprived when compared to this point, but maybe not when compared to that point. Well, I think this is very interesting because these points actually represent historical things that have happened. One is, this is the glacial maximum. The glaciers had pushed all that biomass off the Earth. So, clearly huge areas of the northern and southern hemispheres had been cleared of all their biomass. But I really want to note this one thing that blew my mind when I observed it. This amount of biomass and this amount of biomass are pretty close to the same. Not exactly, but not too far off. And what happened when that biomass was at that level? The glaciers began to melt back. And so, with the biomass at that level, for some reason, the climate began to warm. I'm not sure I can tell you what it was, but I know that now when we have a biomass level about that level, we're experiencing global warming, the climate warming.
You're saying that right now our biomass level is pretty similar to during the last ice age?
Right, right. So these other points are significant because this glacial minimum is also the dawn of agriculture. This curve might have gone up into here before it leveled off, but mankind interfered. This point represents around the 1850s when James Watt improved the steam engine to the point where it became practical to feed wood into your steam engine and let it do your work for you. And the demand for fuels at that point was such that the environment can't keep up.
It's also the Mulberg plow, right?
I guess maybe, yes. Who said that? Yeah. I didn't have that in mind, however. Yeah.
Did the increase in biomass and around that top point also then did the Earth start cooling around that period based on your earlier?
Let me think about that. In general, I think that would be true.
I mean, we're coming out of an ice age, so there was a warming from the Milankovitch cycles, but certainly the vegetation would have put a hydrological cooling effect there. You see that there's evidence
So-
for that.
And this isn't necessarily implying causality. Maybe because the globe warmed, the curve followed. But maybe because the curve was like this, the globe warmed. So I think that's a question worth asking, and it motivated me. So let's go on to the next. I guess I wanted to say, and I made this comment about carbon sequestration, we don't need to get rid of our carbon. We need to replace the order in it. Neither reduced carbon use nor carbon sequestration can rebuild the carbon mass and complexity in the biosphere. And that's what we need to do. Now I just want to look at some energy relationships that drive the Earth. And this is a illustration put together by NASA, and it shows the energy coming in from the sun and the energy radiating out from the Earth, and they're balanced. 340 watts per square meter comes in, 340 watts per square meter goes out. The budget is balanced. This leads some people to say the Earth is in equilibrium. That's incorrect. I may be mincing words, but it's very important to know that that's incorrect. An equilibrium system only occurs in an isolated system. And an isolated system is like this. It's surrounded by walls that prevent energy or matter from passing through the system. That system will approach equilibrium. No other system will. And so the Earth is not in equilibrium. It's in a steady state balance. There's as much energy going out as coming in. But that's not equilibrium. Isolated systems evolve toward equilibrium. Flow systems, which is what this is, evolve toward a steady state. So let's go on with this. I think there's one more slide that talks about this. The Earth is a thermodynamically closed system. And a closed system is defined as energy flows through it. Matter doesn't. So now we know that there's energy from the sun impinging on the Earth all the time and being discharged. But there's no matter except for an occasional, maybe, asteroid that lands in Russia or something, or on our house. And so in the absence of matter flowing through it, the Earth is defined as a closed system. Because the energy coming in is equal to the energy going out, the system is thermally balanced, and the temperature remains approximately constant. You remember we were talking about that balance, and energy coming in equals energy going out, the temperature stays the same. But how does this system compare with an equilibrium system? They are fundamentally different. Systems in equilibrium evolve toward a maximum entropy content, which is equilibrium. That means there's nothing happening. Flow systems evolve toward a more ordered state, characterized by diversity, complexity, order, and activity. And that's why the Earth is so different from any other planet. We are not in equilibrium, nor are the other planets. I could go into that, but because we're in such a state, we maintain this complexity and activity and order. So let's go on to the next. What about entropy flow? Well, this is a similar chart showing the entropy that's coming through the Earth. And you remember a couple of slides ago, we said when this temperature is high, the entropy is low. Well, here's the entropy coming in from the sun. 40 milliwatts per kilogram per square meter. And here's the entropy going out. 940 milliwatts per kilogram per square meter. The Earth is discharging more disorder than you can shake a stick at, and it's not really receiving all that much. And that's leaving order to just grow and grow and grow on the surface of the Earth. That's what Darwin was talking about, really. That's evolution. The entropy budget is not balanced at all. The entropy coming in from the sun is Q over 5,600 degrees, which is the temperature of the sun. The entropy going out from the Earth is Q over 288 degrees. There's 20 times difference there. The entropy balance shows a deficit of disorder, which is a surplus of order. Order on the surface of the Earth increases all the time. That's what causes evolution. Yes?
What's the unit of measurement for entropy?
Well, it depends on the system of units that you use. But here they're using milliwatts per degree Kelvin per square meter.
Yeah, and that was my question too. I don't want to slow you down, but I'm just curious how those numbers get derived.
Yeah, very, very carefully. And of course, if you were measuring this in, BTUs per hour per degree Fahrenheit per, you'd come out with an entirely different number, but it would have the same value.
I just would have no idea how you would measure the entropy going out of the system.
In a way, you calculate it. Go back one slide. 2 slides. You know, this is the amount of energy coming in. And I'd have to go back a couple of slides, I guess. But you remember S equals Q over T? Well, this is Q. And then T is the temperature of the sun. And so you could, entropy is more often calculated than it is measured. So, go on. So, this is the source of order in all flow systems. Since energy flows down a temperature gradient, that is, it flows from a hot area to a cold area, from hot to cold, any system in thermal balance, that is, it discharges the same amount of heat as comes in, discharges more entropy than it takes in. You might have to go over those last few pages to rationalize that, but it always comes in the hot side, goes out the cold side. So there's more of it on the cold side than on the hot side. So the system is becoming ordered. The balance of entropy coming in to entropy going out determines the amount of order the system is going to experience. This results in a tendency for all such systems to become ordered. Now, some systems are not very ordered, but they're not in equilibrium. They're not completely disordered. If these balances are not very impressive, then they're in a rather low state of order, which is the state of all the planets. But the Earth happens to be in this supremely ordered state because the entropy balance works out that way. So let's go on. Okay, this is just a repeat, and for some reason I thought it was relevant here, and it is, but we've seen it before. So okay, so here's the entropy balance concept. Entropy is entering a system. Entropy is being generated by all the processes going on in the system, and entropy is leaving the system. Now, if the entropy leaving the system is more than the entropy entering the system, the entropy generated in the system has got to be positive, because there's more entropy leaving, and it's got to be the sum of these two. If the entropy leaving is less than the entropy entering, then the entropy being generated is not enough to keep up the order in the system, and that number is going to be negative. So what we're saying here is entropy accumulates in the system at a rate equal to the entropy coming in plus the entropy generated within the system less the entropy leaving. If more entropy is leaving than is being generated plus what is entering, the entropy content of the system is being depleted, so the system becomes ordered. If less entropy is leaving than is being generated plus what is entering, the entropy content of the system is being increased, and so the entropy is becoming more disordered. So here's an explanation for the amount of order in a system. That may answer your question. Now, okay, what's an ordered system? Well, this is a diagram of our climate. You know, the solar energy comes in and warms the equator. Just like in a convection cell, the air rises at the equator, spreads out, and does this little circulation loop, and we get a tropical climate zone. And this kind of stimulates another cell that stimulates a temperate climate zone. And the final cell generates a polar climate zone. Now these are 3 separate and distinct climate zones, or 6 if you consider the whole Earth. So the climate on the Earth is an ordered system. That has a lot of implications, both biologically and and thermally. All the life that occurs in this zone evolves into a compatible form with this climate. All the life that evolves in the temperate zone evolves into a form that's compatible with that climate. So you get species diversity based on the climate pattern. And you get a climate pattern because of the entropy balance. So all of these things reinforce each other. So what can I say? Climate diversity in an evolving biosystem gives species diversity. If the Earth were all one climate without a pattern, then the species wouldn't have that many niches to become evolved into. And one of the problems with climate change is we're losing species diversity. If all the world were in equilibrium, it would all be uniform. That's what equilibrium means. Let's go on to the next one. I think okay. I just want to evaluate three types of systems. In this one, it's a low entropy system. The water is in the form of ice. The biomass is obliterated by the ice if the ice is a glacier coming out over the surface of the Earth. The glaciers grow, the biomass diminishes. Now, when the biomass diminishes, we just saw two examples where the climate warms when the biomass diminishes. So if that happens, the climate warms, the glaciers retreat. And then the climate kind of cycles back to where it was. And we get this cycling back and forth effect. If we have a high entropy system, the water exists as a vapor. The vapor is not really available to plants anymore. Deserts expand, biomass diminishes. When the biomass diminishes, we saw that the climate is warming again. So that encourages the deserts to expand some more. And this doesn't cycle. It results in continuous and accelerating warming. That's bad for life on Earth. When the destructive force is mankind, we just obliterate the biomass. Biomass is reduced. When that's not our reproduction, by the way, that's biomass reproduction. When the biomass is reduced, it obviously can't reproduce. So the climate warms again because that's a diminishment in the biomass. Deserts expand, and we create a continuous and accelerating warming too. So none of these are good for life on Earth. This is the cycle that's good for life on Earth. A little bit more. We're almost there. Well, global warming is when the energy coming into the Earth is greater than the energy exiting the Earth gets warm. That results in global warming. And what I'm proposing is a little different from global warming. So let's go to the next. What I'm proposing, I'm going to call global equilibration. What we've done is we've favored one entropy, one energy transport system over the others. The atmospheric heat transfer machine changes in respect to the size and violence of the order it creates. And these order mechanisms create order with less resistance than than they had. So the climate differentials diminish under those conditions. When the heat transfer mechanism changes, the diversity of the climate changes. And so the globe is more likely to become all one temperature. Now we can go to the next one. When that happens, the average temperature is about 59 degrees. Well, what does that mean? That means all the ice in the world melts. That means all the temperatures in the temperate and polar zones all increase. The temperatures in the tropic zones don't seem to increase very much. They might even cool off a little bit. But that's really, we don't have tropical zones complaining about temperature. They're complaining about ocean rise. So this global equilibration looks an awful lot like global warming. But it requires no change in energy flow through our system. So it's a very important part of the global warming equation. My wife is telling me has a shepherd's crook here. Yeah.
Isn't it, we do know, right, that more energy is flowing in because it's not able to escape. So why does, right? That's one mechanism leading to what we're observing. So you're not saying that mechanism is not correct?
No. I'm just saying let's expand our view and see what other mechanisms might be causing this.
I think you need to just go over the implications of that slide you have up. Is that they're dramatic for human life on Earth?
Yeah. This is an equilibrated climate without any patterns. This is a climate with 3 different climate zones in each hemisphere and patterns that lead, by the way, to wind patterns that are trade winds, carry commerce and carry the weather and lead to different temperatures at different parts of the Earth. This leads to a whole list of characterizations on the Earth that would all be wiped out if the Earth equilibrated. And it doesn't have to equilibrate all at once. All it has to do is approach equilibrium.
Which is what we're doing.
Yeah, that's what I contend. See now, there are different changes that can occur that affect very greatly the way the Earth transmits heat back and forth. If, for instance, we have phase changes, as we did in the ice ages, ice doesn't flow as easily as water does. So all of a sudden, there's a lot more resistance to heat flow. So the ice ages might actually encourage the temperature differential here. But at the end of the ice age, all of a sudden you bounce back to this again because the ability of the oceans to transfer heat by liquid flow is much more greatly enhanced. I've had arguments, I think, with you, Henry, about if this climate zone, it's been demonstrated that as the globe warms, these interfaces between climate zones move northward. And if this differentiation moved northward all the way to the pole, all of a sudden this climate zone would be eliminated, and this rising air mass would be at the pole. And this produces precipitation all along that line. All of a sudden at the pole, you get a lot of precipitation. That generates glaciers. So this could be kind of cycling back and forth between a condition that generates glaciers and a condition that makes it a desert, which is what it is now. So in order to produce more entropy more rapidly, the Earth becomes more ordered all the time. What I haven't said really is ordered systems produce entropy faster than disordered systems. Mechanisms that enhance energy flow lead to equilibrium. Mechanisms that oppose energy flow lead to differentiation, order, pattern, and structure. Let's go one more slide and I think I'm finished. So Mother Earth produces more biomass and more glaciers to become more ordered. We need to help her out by creating the conditions that enable her to do more of the same. These conditions can be created by large-scale afforestation projects, ecosystem restoration projects, soil carbon reclamation projects, etc. But it's a whole different rationale.